Yeah.
Hello. Well, good evening, everybody. We're already late for 4 minutes. Well, if you wonder, we're full house tonight. Those seats are reserved. What I mean is we have some friends who will be watching online. So they could hardly come, but they can have us on webcast. So I will be your host for the evening, and I will be assisted by Paddy Sheridan later on. And on behalf of the Mechanical and Manufacturing Division of Engineers Ireland, as well as the Institution of Mechanical Engineers of the Republic of Ireland region, we welcome you to this presentation on multifunctional heat pumps. First thing first, we have some house rules. Now, in case of emergency, we try not to panic. We have 2 fire exits, one on my left, that is, we have a green man above it, and we have behind you there. And also, it is now is the best time for me to ask you to turn off your mobile phones, just in case you have not done so. We don't need it. And this presentation will last for an hour, and we will have 15-minute question and answers afterwards, towards the end. Our guest speaker for tonight is Peter McMahon. I first met him in a National Construction Summit in City West last January of 2019. And he has over 30 years of experience, starting out as a refrigeration service engineer, then advancing to achieve the refrigeration technician certificate in 1995, then progressing to service manager and director in partnership until eventually establishing the European Industrial Chiller Limited, or EICL, in 2004. Peter was also a council member of the Institute of Refrigeration Ireland for 7 years, including being the chairman of the membership committee, as well as a member of the technical committee. Most recently, Peter returned to TU Dublin Technological University to study building engineering, and he is on his 3rd year part-time this September. At EICL, Peter has a team of HVAC solution engineers who have achieved some very notable successes, which include securing the HVAC orders for the National Gallery, the new Central Bank of Ireland, and most recently the new Setpoint Village and Salesforce building. By the way, the Setpoint is at the moment the highest office building in Dublin. It has 17 stories. If you are there, you can see the beauty of the keys. Now, these successes are very much a direct result of their HVAC solutions based approach, with the focus being upon energy efficiency, using the very latest technological innovations, including intelligent free cooling and multifunctional heat pumps. So gentlemen, please welcome Peter McMahon.
Thank you, ladies and gentlemen, and Orlando and his colleagues at Engineers Ireland for inviting me here to give this presentation. I genuinely believe you will get a lot of value from this presentation. I'm going to explain about multifunctional technology, a little bit about energy efficiency, how the calculations are worked out. And I think even if you take on board maybe 25% of what I tell you here today, you will go away with a lot more knowledge, hopefully, than what you've come away with. My background slide, I hope you see, depicts a city centre, Dublin in this case. And the relevance is to help you imagine the amount of buildings in all the cities around the world and the energy being consumed. And unfortunately, very often, very, very inefficient. As building engineers or even mechanical engineers who have input into building engineering, you guys have a major part to play. You can do more than the vast majority of the population of the world. So you have a responsibility, I believe, as do I, to do all we can to reduce the energy consumption for our clients. So my objective is to bring value to you, and consequently you bring value to your clients. And that's really what this is all about. So I'll kick off just briefly going over the agenda. So as I said, we will explain a little bit about energy efficiency and calculations. We'll go over a very brief history of air conditioning HVAC systems. Of course, I will explain about the NRP multifunctional heat pump technology and associated products, because we're talking about 4-pipe systems here where you have heating and cooling. I'll brush over fan coil units as well, just to give you a little overview of things you can do to improve systems. Because like I said, this isn't just about a particular product, it's about systems, it's about how you can integrate this technology into HVAC systems. Okay, first of all, why bother? Well, I think even Trump these days accepts we have an emergency. He mightn't say it publicly, but I'm sure he does. Especially with Storm Dorian there in the last week or so. So it is the global emergency of this century, and we do have the potential to do a lot to reduce this. There is global warming, and it's created directly and indirectly, but it all comes back to the buildings, manufacturing, and what we can do. So I'll briefly just go over how the global warming can be created. So like I said, we have direct effects from refrigerants. So you have various refrigerants, and there's a lot of talk about GWP and how we should use low GWP refrigerants. Of course, we should use as low GWP refrigerants as we can. However, you should be aware as engineers, there's a bigger picture. Sometimes equipment such as chillers and multifunctional heat pumps, perhaps, that use a lower GWP don't necessarily have a better efficiency than a chiller with an older refrigerant. So the point being, take a look outside the box. Don't just look singularly at the refrigerant GWP. Okay, so it's worth getting that point across. And of course, the indirect effect then, the CO2 that's being generated from inefficient equipment. So again, that brings us back to, we want to do all we can to make systems, HVAC systems, as efficient as we can. So by choosing to become a building engineer, you have a responsibility. And our objective, like I said, is to help you with that responsibility to reduce climate change and, of course, do our bit for the environment. So how are we going to do it? So firstly, let's just push over EER, Energy Efficiency Ratio, and ESEER, which is part load efficiency. There was a level playing field created. So Eurovent is an organization where the manufacturers can submit their products. So you should look out for the Eurovent symbol on the catalogues of the equipment that you're considering to use. If it's not Eurovent certified, there's no independent verification. It does what it says in the tin. So the first point I'd say is try and make sure you have an independently verified product in the equipment that you're going to use. As part of the level playing field, they needed to create a set of nominal conditions. So with chillers, we have a normal chill water set point of 7 degrees C, typically with a 5 degree delta T, so supply 7, return 12, in an ambient of 35. Because remember, these catalogues go to countries all over Europe, and they just use a set of nominal conditions for all the countries throughout Europe. Equally, for heat pumps, we need a set of conditions. So they normally work with a condenser outlet of 45 degrees C, again a 5 degree delta T, so coming back at 40, and a dry bulb ambient of 7 degrees C. Like I said, if you look at the catalogues, you will see an absorbed power. Let's see if this pointer works. No. Yes, okay. So you will have model numbers typically in a catalogue, and you will have absorbed power. And if you divide your cooling capacity by your absorbed power, you will have an energy efficiency ratio. Okay, I'll go to that a little bit more in a minute. You will also typically have an ESEER on the basis that it's using the Eurovent formula, which I'll explain now in a minute. There are various categories or classifications for the energy efficiency ratios. So you can see your A to G, and there are variations from air-cooled, water-cooled, or remote condenser. So of course you're aiming for the A category here. Now, having said that about EER, it's almost irrelevant, because ESEER is a calculation, again, it's a Eurovent formula, which I'll show you now, which takes into consideration part load efficiency. As we know, chillers and heat pumps rarely run to 100% load. So the part load efficiency is much more important than just your EER at 100% load. Engineers have to size for the hottest day of the year, solar heat, bodies in the building, lighting, and so on, and a bit, percentage of margin. So like I said, they typically don't run to 100% load. So part load efficiency is much more important. So this is the formula. So as you can see, it's what they call a weighted formula. And we can see that we assume at 35 degrees C ambient, we'll be at 100% load for only 3% of the year. At 75% load, when the ambient drops to 30 degrees C, at 33% of the year, and so on and so on. So it's a calculation that takes into consideration as the ambient drops, the load drops, and the percentage of operation varies depending upon the load. When all the data from the manufacturers is put into this formula, you get an ESEER figure. And that's, like I said, much more important than your EER figure. If there's a water-cooled unit as opposed to an air-cooled unit, they have a formula as well, just using slightly different temperatures, as you can see there. If you are representing a client from America, for example, they may use an other variation of your energy efficiency classification, such as IPLV, integrated part load value. So a lot of our consultants that are working with American clients would ask for the IPLV value, which of course the manufacturer should also be able to give you. Now, we're talking about part load efficiency, so we can't really do this without talking about different types of compressor. So as you can see here, we have Copeland Scroll, manufactured in Cookstown, Northern Ireland, by the way. A lot of people don't know that. One of the biggest manufacturing bases for Scroll compressors. We have screw compressors. You can have non-inverter or inverter screw, and there is a difference in performance. And then you have turbocore, which have really good part load efficiency. But I'm going to show you a couple of curves just to explain that. If you look at, let's say, these slides are quite old because this is an Engineers Ireland approved CPD. I need to stick to the correct slides. I'd like to update it, but I'd have to resubmit it and everything else. So for the moment, it'll serve the purpose. So the point being, you could have, oops, my apologies. You could have a screw type chiller, and you could have a scroll type chiller. And the screw might look like it has a better performance because the EER is 3.1. Like, these are just examples, by the way. And the scroll might have an EER of 3. So if you're just looking at your EER, you would be wrong. You shouldn't just look at your EER. You should look at your ESEER. Because when we look at the part load efficiency, you can see there are completely different part load performance curves. Now, this is really important because as you can see, now this is just a sample, by the way, because the part load performance curves will vary based upon the country, the ambient conditions, or the ambient profile, the climatic profile of the location. The load profile, you might have different load profiles with different temperature set points. But this is a good example of how the part load performances can vary. So if we look at the scroll type curve here, you can see it's a nice steady increase in performance almost throughout. If we compare it with the non-inverter screw, we can see that drops off. The inverter screw is much better, it keeps rising, and the turbocore is pretty much off the chart. However, if you have, I know some of you guys are involved in manufacturing, so if you have a manufacturing plant and you buy a turbocore chiller that has excellent part load efficiency, you're never going to get the benefit from that if you size it to run at 100% load. So you're much better off oversizing it and running it at low load, but they are more expensive, or you simply go with the likes of a scroll type chiller because you will still have very good part load efficiency, and they can be all somewhat similar at 100% load. Okay. Now, with the knowledge that that chillers are typically at their least efficient at 100% load, as you saw from the graph there, there is no logic in running chillers really up to 100% load. this is really the way HVAC systems were designed historically. You would nearly always have one chiller as your lead chiller and a standby chiller. And if one chiller went into alarm, it gave a signal to your BMS system and it would enable the standby chiller, with little or no consideration for the part load efficiency. So manufacturers such as EICL, obviously I'm going to talk about EICL because we represent EICL, but I'm sure a lot of manufacturers will come up with the same technology if they haven't already. When they understand this logic, they say, why do we run up to 100% load? Why don't we create a technology or a software package that understands the load profile and will optimize the efficiency of the system? So if you have a chiller that was on standby, there's no sense in running one chiller up to 100% load. So what they do is they've created this software package where your BMS now only enables what's called a multi-chiller sequence controller. The multi-chiller sequence controller is programmed with algorithms based upon the performance curve, very specific to the compressor technology in the chillers within the system. So, for example, the new Central Bank of Ireland is a project we did with O'Connor, Sutton Cronin and Winthrop, and it was a BREEAM project, so it was a very high efficiency building, and they wanted the best of the best. So we recommended the multi-chiller sequence controller. They have two approximate 1.1 megawatt inverter screw chillers with free cooling technology, and then they have one smaller 270 kilowatt chiller, again free cooling with scroll compressors for night time. So instead of having massively oversized chillers short cycling at night, they have the smaller scroll chiller for night, and of course they have free cooling technology again because ambient temperature drops at night. So again, that's worth keeping that in mind because free cooling in Ireland is a really good option for HVAC systems and process cooling applications as well. Okay, so the logic there is that the multi-chiller controller communicates with the controller of each individual chiller based upon the compressor technology and will optimize the efficiency of your system. So if chiller number one, for argument's sake, is getting up to, let's say, 70% load and the efficiency is dropping off, it knows I'm now better off to enable my second chiller or third chiller and so on. I think we can connect up to about 9 chillers on one system, more than you typically have in any system. Okay. It also monitors your common inlet temperature and your common outlet temperature because it's monitoring your delta T, because there's a direct relationship between your delta T and your load. Obviously, as the temperature coming back is increasing, your load is increasing. So it's monitoring your load and it's communicating with the chillers, and you now have a much more efficient system by simply integrating a piece of hardware with an intelligent software program in it. And that's the first component I'd like to stress to you guys tonight. There really isn't a new HVAC system or process cooling system that has 2 or more chillers that should be put in without a multi-chiller sequence controller, regardless of the manufacturer. Okay, as long as they're using the same intelligent software that we are. Okay, that's just to visualize. It's all very neat touchscreen nowadays. And as I mentioned, it can be integrated with all different types of compressor technology. Okay, so a brief overview of the history of HVAC. Historically, VRF systems were very popular, cheap, cheerful. I'm not going to go into all the pros and cons, but let's just say pumping refrigerant into a building isn't as widely accepted nowadays as it might have been many years ago. Also, it's worth considering the cost of refrigerant has just, I think it's more than quadrupled. It's gone out of control. Countries have quotas in relation to the volume of refrigerant that they can bring in. There's all these new refrigerants coming into play, as you guys know. So historically, it was a very competitive option. I don't think that's the same anymore. Water-based systems, ethically and ecologically, I think are the way to go. With water-based systems, historically, you would have had a boiler for your hot water and you would have had a chiller for your chilled water. And let's say, for example, you have a glass, all these office block buildings are glass faced now. Although I know we're trying to put pressure on architects now to change their design because of the solar heat gain and the amount of energy that's having to be created in their HVAC system to deal with that. That's another topic altogether. But historically, you could have had a glass surface building, which on a nice sunny winter's morning on the south side would have had cooling required, and on the north side had heating required. And consequently, we had a chiller running away And as we're cooling water, we're taking heat through refrigeration and we're dumping it from the condenser at the top of the chiller. And at the exact same time, we could have a boiler banging away in a basement or a plant room generating heat. So the whole purpose of the multifunctional heat pump is to try and regain that energy and utilize it. So that's what we're leading on to here. Your 4-pipe heat pump system is designed pretty much the exact same as you would with a chiller and a boiler. So you still can have your 4-pipe fan cool units, your heating valve and your cooling valve as you would be used to. This is an example of a load profile. It's just a sample example. A consulting engineer gave me this recently, and it's a really good graph to highlight how the load profile can change from, you can see your heating here in your winter, spring, dropping down, of course, in the summer, and then, of course, back up in your autumn and winter. And, of course, vice versa, your cooling will typically go up in the summer and back down in the winter. As you can see, it's worth pointing out, the heating load is lower now than the cooling load. So this has completely changed from years ago. Years ago, we had buildings that were, let's call it, leaky. So you would have had a much higher heating demand than cooling demand. That's completely flipped on its head now. So now we're much more concerned about the cooling load than the heating. And I'm going to come on to why that's important now in a minute. So firstly, let me just explain about the multifunctional heat pump. We'll go through the features. There's ranges typically in the AirMech range from 50 odd kilowatts to about 500 kilowatts. This is your cooling capacity. Your heating capacity is typically higher using nominal conditions. Of course, that changes if the conditions we operate at are different. There is a specific reason why we recommend more smaller multifunctional heat pumps, but like I said, I'm going to come on to that in a few minutes. The features are pretty much like you would have in a chiller or a heat pump, with the exception of 4-way valves and very intelligent software. So you have your compressors, you have your condenser, you have expansion valves, and you have an evaporator. And of course, the 4-way valves. Our multifunctional heat pumps have scroll compressors with 410A refrigerant. Okay. You can get them with integrated pump and tank sets, expansion vessels and so on, basically the hydronic kit. I do recommend you get the multifunctional heat pumps with the pumps integral on both the cooling side and the heating side. And again, there's a very important reason behind that. I'll brush over it when we're going through schematics in a while, but please do take note of that. The operating limits, more than adequate for Ireland. So you can see here, we can cool from 4 degrees C up to, 18 degrees C in an ambient of, what are we at, 35 plus there. By the way, the National Gallery of Ireland, we put in multifunctional heat pumps, and we have that with multiple set points and different modes of operation for ice making mode at night, and we actually provided that where it can make ice at, well, we can provide chilled water, chilled glycol at -6 degrees C. So now that was a special, but we can do that if necessary. Okay, so the schematics, how do they work? So let's just go through the 3 modes of operation here. So again, like I said, we have our compressor. This is cooling only. We have 2 circuits. We will always have 2 refrigeration circuits. And in this case, both circuits are serving cooling only. So you can see we have compressor pumping through our condenser, go through our liquid line, expansion valve. You will have low pressure, low temperature, liquid refrigerant going through the evaporator. Obviously, the refrigerant evaporates, and we have low pressure, low temperature, vapor going back to your compressor. Very quick run over refrigeration cycle there, if anyone doesn't know. Okay. Now, when we're working cooling, we have a term called EER, which we spoke about a few minutes ago, energy efficiency ratio, which is about getting as much out for as little in. Okay, one divided by the other is your EER, as you know. COP, we use the term coefficient of performance for heating as opposed to EER for cooling. It's the exact same formula, what you get out versus what you put in. So now you can see we are pumping from the compressor hot gas, high pressure, high temperature gas through our recuperator, which is acting as a condenser. So that's heating our water. We've both circuits doing this, going through this heat exchanger.
We will then have our refrigerant coming out of the condenser through our expansion valve. The condenser has now become an evaporator, so we're getting our source from the ambient air. Okay, so as you guys may know, as the ambient air drops, the efficiency drops off, but most people would be aware of that for heat pump technology. So you need to allow and size your equipment for a low ambient temperature, so it'll work in low ambient conditions. Okay, and again, what you get out versus what you put in is your COP. Now, the new term TER, total efficiency ratio, a lot of people won't be familiar with. So what we're doing here is we're pumping our refrigerant through the condenser first, heating the water. We are then pumping it on through the evaporator, cooling the water. So we have simultaneous heating and cooling. The condenser or evaporator, as they were, depending on the mode of operation, is now out of the circuit. It's out of the equation. So we're now just transferring heat, where we take it from cooling the water, we're transferring it to the recuperator where we're heating the water, and we're simply transferring the energy. So let's use the example of, let's say this is a 100 kilowatt compressor, for argument's sake. And let's say we are giving 300 kilowatts of cooling. We have an EER. I normally ask people, but I won't here now because we're doing a live webcast. So normally you have what's called an EER, your energy efficiency ratio, and you will, if you have 300 kilowatts of cooling, you have 100 kilowatts of absorbed power. Your EER is 3. What you get out versus what you put in. If we were talking about our COP, it would typically be a little bit higher. Let's say 350 kilowatts for the 100 kilowatts of absorbed power. If we are now still using the same input power, but we're now giving, let's say, 300 kilowatts of cooling, 350 kilowatts of heating, our TER, total efficiency ratio, we're getting 750 kilowatts of useful duty. For the same input power, our TER is 7.5, and that is realistic. Now, having said that, if you recall, I showed you a load profile. In reality, you will never have 100% heating and 100% cooling at the exact same time. So in reality, it's intermediate seasons where they're overlapping, autumn and spring, that you may have simultaneous heating and cooling, and it won't typically be at 100% load. But you are basically getting your free heating or your free cooling, depending on which way you look at it. So it's useful energy for free. That really is what the benefit of the multifunctional heat pumps are. Now, I'll show you how we can improve on your system by integrating other products into this HVAC system as well. Okay, so that's the basic 3 modes of operation: cooling only, heating only, and simultaneous heating and cooling. That is an example of a selection that I did for a multifunctional heat pump. And as you can see, you have 500 kilowatts cooling capacity, 640 kilowatts of heating capacity, 150 kilowatts of absorbed power, and almost exactly as I suggested, about 7.5 of a TER. Okay, so it's much greater than you'll ever have with a chiller on its own or a heat pump on its own. If we were to compare historically a chiller and a boiler, your old-fashioned HVAC system design, with a multifunctional unit operating under the same conditions, you have typically about a 20%, 26% energy saving. These are just different locations around Europe, but in Ireland, similar to London, we have, as you can see, a very healthy energy saving there. Naturally, there's a consequential saving on CO2 production. There's always a knock-on saving there. Okay, it's worth mentioning intelligent defrost. A lot of people were concerned about the defrost cycle. Historically, defrost cycles weren't very intelligent. They were programmed to come on maybe once an hour, twice an hour, every 15, 20 minutes, whatever, with little or no consideration for if an actual defrost was required, or it would come off before it was actually finished in the defrost cycle. Nowadays, with the software and with the monitoring equipment that we have, we can enable a defrost really only when it's actually required. So we're monitoring our evaporating temperature, our suction pipe temperature, and our ambient temperature. And we know that we only have to, or we can only enable it when we require, when it's actually required to be enabled. And similarly, it'll come off when it's actually required to go off. So we're not wasting energy enabling a defrost when it's not actually needed. So we've moved on leaps and bounds in relation to the defrost technology there. Setpoint compensation is a really good feature. Again, it's another component that is added into the software of chiller controls or heat pump controls or multifunctional heat pump systems. Again, historically, we design chillers with a supply of 6, return of 12, or maybe 7 and 12, with little or no consideration for the actual load. With boiler systems, people have used weather compensation for years. Why don't we do the same with chillers? Well, historically, you may say, right, well, I need 6 degrees for dehumidification, but do you need it year round? And typically you don't. So as the load is decreasing, if we can afford to bring our set point up a degree, why not do it? Every degree you go down in your set point of your chiller, you will see a drop off on your performance and your efficiency. So we've done this on the NUIG in Galway with BDP not so long ago, where we had a direct relationship between the ambient temperature dropping and our set point increasing. So that's a really useful feature that I would strongly recommend. If we introduce this just on chillers, you're going to save energy. If we introduce it on chillers with free cooling, you're going to save a lot more energy. Because let's say you have a fixed flow rate, for argument's sake. Now you can look at variable flow rates, that's another story altogether. But if we look at fixed flow rates with a nominal delta T, with every degree increase in our set point, of course the return temperature is also increasing a degree as we go. So every time you increase your return temperature, you are improving the potential for free cooling. So it makes a massive amount of sense to do that. And like I said, we're doing that with the technology in the new Central Bank of Ireland and the new ExoPoint Village buildings that are going in there. Okay, I've already explained about the intelligent software, smart controller, the user interface. Nowadays, of course, we can remote log in with the National Gallery. They wanted us to have remote monitoring. So we could simply, in fact, on my mobile phone, I was able to just log into an app and I could see exactly what was going on site with temperatures. So nowadays, there's remote interface capabilities there as well. Of course, you can just log into BMS by Modbus or BACnet as well. Okay, so system design. As I said, you design your system as you would historically, a typical 4-pipe system with a few benefits. So this is a sample schematic to highlight how we can integrate other products. So just to recap, you can have a chiller cooling only, or a multifunctional heat pump cooling only. You can have it heating only, or you can have simultaneous heating and cooling at the same time. Now, let's say you have a domestic hot water requirement, as a lot of buildings will have, or hotels in particular will have, but they will only have it at periodic times. So in the morning and in the evening, maybe a bit throughout the day. So you don't want to design your multifunctional heat pump with a 65 degrees C set point, as you would have started with a boiler. Because the higher the heating set point, the less efficient your multifunctional heat pump will be. So we'll design it for comfort heating, maybe 45 degrees C or thereabouts. And we will add on a water-to-water booster. So this is basically just another heat pump, water to water, but dedicated to your domestic hot water requirements. So let's say, even if we give the example of peak summertime a couple of weeks ago, I think we're losing it now, where we have a high cooling load, little or no heating load, but you do have a domestic hot water requirement. Historically, we would have brought a boiler on. Now, as I said, peak summer, we would have been dumping all that energy to the environment. We don't have to do that. So if we bring on our water-to-water booster, so domestic hot water requirement enables our water-to-water booster, says, right, I have a requirement for domestic hot water, comes on 6 in the morning or whatever. Remember, a water-to-water booster has an evaporator and a recuperator. As this comes on, the temperature will drop here. This, heats on this side, cools on the other side, that's your evaporator. That is circulating your water back to your multifunctional heat pump. It automatically detects a drop in temperature. So instead of dumping the energy through your condenser, it realizes a drop in temperature here and simply diverts the refrigerant to the recuperator. So now instead of dumping that energy, we're giving it to the recuperator for free. Okay, free energy. You do, of course, have a pump that's circulating. It's worth knowing, so you do have an absorbed power there. But when you start talking about hundreds of kilowatts or megawatts, a couple of kilowatts of a pump becomes pretty insignificant. So we're taking that energy down here to our heat pump, and you now have a very high temperature source for free. Okay? So the point I'm making here is if we integrate multiple components onto the same system, you're going to massively improve your HVAC system design. Okay, we can, of course, add on, this is just a sample schematic, your air handling units, your fan cool units, there's loads of things we can do there. And I'm going to tell you just about one or two more. Can't give everything away today. But do come back to me afterwards if you want to know a bit more about this. Okay, so another really good component, I was actually talking to a consultant a little while ago, and they were trying to develop this type of system. And I said, we already have it. It's being designed, it's being developed. Save yourself the trouble. Package ready to go. So let's say imagine you have a 4-pipe system. Historically, you have 3 rows for your cooling coil, and you have 1 row for your heating coil. Your cooling coil, as I said, was typically served with chilled water 6 and 12 or 7 and 12, and your heating coil typically from the boiler 65 degrees C. Now imagine if we connect our hot water, let's do away with our heating coil, right? That's gone. We only have a 2-pipe cooling coil now. So imagine you connect your hot water to your cooling coil. As I said, there are 3 rows as opposed to 1 row. So these are copper tubes, aluminium fins, typical fan coil unit. You now have 3 times the surface area that your hot water is going through. Consequently, do you need your water at 65 anymore? The obvious answer is no. So we can drop our temperature dramatically. We can connect it to our multifunctional heat pump, get our source for free. Not always, by the way, because in the winter time, you could be using that, so you need to add that on. You do need to be aware of that. But again, like I said, if you come to us afterwards, we'll explain all this in a bit more detail. But the point here is if you now use a simple valve kit, this is called a VCF X4 valve kit. It's manufactured to fit directly, of course, onto the AirMech valve kit. You could manufacture this yourself, of course. Consultants were looking at it. They were looking at getting contractors to build it. And of course you could do that. But we can get these factory made, factory fitted in bulk for, you know, a very competitive price, let's say. So the point being, you're going to massively improve the efficiency. It's almost like having 3-row heating coil and a 3-row cooling coil in one unit. So efficiency, fan coil unit cost, it's obviously cheaper to buy a 2-pipe fan coil as opposed to a 4-pipe fan coil. Space is also saved sometimes, not always, it depends on the model. The valve kit, it's cheaper to buy and cheaper to install, as you can imagine, than manufacturing this. And the time of installation is much easier. So a very, very simple valve kit can massively improve your efficiency as well. Okay, so it's worthwhile adding that into the presentation. Of course, fan coils you can get in all shapes and sizes. In Europe, for example, around Italy, I'm over in Italy on a regular basis, you'll see the wall-mounted or floor-mounted. They're very common. Even very plush hotels, that's what they would typically have in restaurants and so on. In Ireland, we tend to have the ducted type, P, I think it is, yeah, down the bottom right there. We're typically ducted in Ireland, hotels, offices, and so on. And of course, nowadays, it's all EC fans, and you've typically about a 50% reduction in energy consumption with the modern fan coil units. You can get a control system. Of course, most systems nowadays would, or most consultants would work with a BMS supplier, and they would have a BMS system to control everything. We can offer a control system as well, if required. Applications nowadays, like I said, is pretty much everything. You know, your hotels, your office blocks, your factories. There's the Copeland factory, your National Gallery, and so on. That is it. I hope I am on time, because I am conscious that we have a football game tonight, just down the road here. So yeah, we've good time if anyone needs to get there. So, thank you.
Thanks, Peter.
Just before I finish, can I just mention, I do technical vlogs. I'm delighted, by the way, that I've come here, because I'm hopefully reaching a wider audience of engineers with the webcast. We do the rounds, we go to consultants, we do our lunchtime CPDs, but as you can appreciate, it takes a very long time when a new piece of technology comes out to get around to everybody. So to try and save a bit of time, I do vlogs, technical vlogs. So I have my own YouTube channel. I don't think I'm going to make it to Hollywood. But when something new comes out, I'll record a 2 or 3 minute vlog. I do compress it as much as I can because I know people don't want to watch hours and hours of stuff. So connect with me on LinkedIn and you'll see the vlogs that I throw up there on a regular basis if you're interested. Thank you.
Thank you, Peter. Thank you very much. Very informative. And gentlemen, as we've no ladies, we have some time for a few questions. If there's anybody that would like to kick off with a question for Peter, just raise your hand. And
you mentioned climate change a few times and the
yes.
ethical prospect of going towards water as the coolant rather than the typical refrigerants.
Yeah.
What technologies are coming down the road, or what would you advise in terms of companies to introduce heat pumps or CHP type systems? Yeah.
There isn't a one size fits all. There are various solutions for various applications. So if a client gives us a load profile and we can download the climatic profile for the location, load profile is really important. If we understand what we're trying to achieve in relation to heating and cooling and when, it enables us to suggest a better solution. We're very much a solutions provider, so it's not a case of there's a chiller, there's a heat pump. It really is about looking at the application and trying to understand what's best. We do, well, AirMech have an energy simulation software package. We can input the load profile, the climatic profile, and we can analyze different types of technology. So we can look at various solutions if required. But free cooling should not be underestimated. Free cooling in Ireland is a really good solution. Of course, multifunctional heat pumps, are an excellent solution. But again, it's a matter of looking at the application.
One of the applications you mentioned was -6 degrees in the National Gallery.
Yep.
I was trying to figure out why do they want -6 degrees?
Cheap electrical rate at night time. Okay. So at night time you have a lower electrical rate and you can avail of that. It's not just as simple as the electricity rate is cheaper. The efficiency of a chiller at night time, or even a multifunctional heat pump that's operating in cooling mode, is much more efficient as the ambient drops.
So you might imagine that abattoirs or food companies might want the refrigerated systems like that.
Yeah, absolutely. We're seeing more inquiries from the likes of cheese storage, dairy, pharmaceutical, certain applications where historically you may not have been looking. They would have had big industrial ammonia plants, for example, and they mightn't necessarily want to use refrigerant anymore. So water-based solutions are being considered much more now than they were.
In terms of bringing the energy down, in that you've got the refrigeration cycle, but are there thermoelectric elements in there as well?
No. An interesting product. I actually had one of my kids look at thermoelectric generators for a project in school. No is the answer. We're not looking at that technology at the moment.
And the other one I mentioned is the shape memory alloys. I don't know if you've come across that.
What is it?
Shape memory alloy.
No.
For extracting heat.
No,
Okay.
No, you have me there.
Okay.
No, I haven't come across that one yet.
Okay.
I'll have to look it up.
Okay. So
it's always good to hear something new, though.
Okay.
any more questions, sir?
With the new building regulations and the NZEB regulations, with buildings having to achieve 10 or 20% renewable energy,
yep.
Would you have any experience in designing for those conditions?
Absolutely.
How would you meet those?
Almost every single inquiry from the consulting engineers nowadays is about achieving NZEB. Part L, 2017, TGD Part L, it was 2017, came in January this year, I think, wasn't it, 2019. 20% renewable by 2020, I think. This is slightly political, so I have to give you a diplomatic answer here. The issue is technology is moving on quicker than the regulations. We're trying to achieve guidelines that the SEAI are putting out there, and there's boxes to be ticked. We have technology, like we're at the cutting edge of technology. We're representing one of the biggest manufacturers that invest millions every year in R&D. They've things that they've developed that we don't even know about that they're trying in-house as prototypes and so on. I get the odd word of what's going on. And I go to the trade show Milan every 2 years because it's always really good to go there to see not just what Airmac are doing, what all the competitors are doing as well. But, okay, to answer your question, yes, we do. It's not as straightforward as you might think in relation to just, again, providing a single product for a single application. The SEAI don't have a system to accept multifunctional heat pumps as of yet. So they have, I know a lot of consultants use the IES software. I'm no expert on it. They input, I believe, information in relation to the building fabric, your U values, your loads, and what technologies they're using, whether it be solar, PV, or heat pumps. And I just don't think it's black and white as use a heat pump, use solar. And they have the consultants are telling me that they sometimes struggle to get a certain product. Or see where we're talking about giving free heating that we've got on a multifunctional heat pump. I don't believe there is a system to accept that through SEAI as of yet. I'm just telling you the feedback I've got. So it's a bit of a shame. We've all these new technologies, but I just don't think the regulations are quite up to speed with the technologies. It's a little bit cart before the horse, but that's just what we have to do, I'm afraid.
Any more questions? Alan has
it. Just wondered, in a domestic type heat pump where, you have this 4-way valve and maybe you can switch it to cooling,
yes,
as opposed to heating.
Yep, absolutely. Yeah.
But you regard the multifunction system as one that can simultaneously give heating and cooling.
Yeah, so we're talking about a 4-pipe system. If you're talking about domestic air-to-water heat pumps, or even water-to-water with geothermal perhaps, they're 2-pipe systems. They're heating or cooling. Yeah. It's like your old-fashioned air-to-water heat pump some people might have put on buildings, but it's all heating or all cooling. Whereas we have 2 heat exchangers, one dedicated to heating, one dedicated to cooling. So we can give you either or, but it's for a 4-pipe system as opposed to a typical 2-pipe on a domestic application.
Yeah. And is it, where you talked about simultaneous and having a TER of maybe 7.5, yeah. Does it have a bias one way or the other?
No, it's all automated. You have a set point for your cooling, a set point for your heating, and it will simply operate to satisfy the requirement. What is really important, and what I would have very quickly skipped over, we tend to discuss it in a little bit more detail. Selecting multifunctional heat pumps and sizing them is very, very important. You don't, because we have 3 modes of operation, as we said, cooling only, heating only, and simultaneous. Every time you change the mode of operation, you're off cycling. You have a time delay to allow for the gas pressures to equalize out. We're doing this a very long time. And when the first ones were put out many years ago, when they didn't allow the time delay for the gas pressures to equalize, you got a bang. Which obviously isn't very good for your heat pumps. So, but like anything with new products and prototypes, you learn very, very quickly. So the manufacturers dealt with that very, very easily by simply putting in a time delay, allow for a little bit, and I think they might have a bypass valve as well. So they allow for the gas pressures to equalize out. But the point being, you have that time delay, you're changing mode of operation, and it's not like a chiller that's just cooling on or off, or a heat pump that's on or off. You could be going from cooling to heating to simultaneous heating and cooling. And every time you have that mode change, you have that time delay. So it's really important that you don't massively oversize a multifunctional heat pump. It would be a bad method of selecting heat pumps. So I think I briefly mentioned you're better off to select more smaller heat pumps and you size them. Remember where we had our overlap with our heating or cooling? You typically size for the peak heating demand, not the cooling, because as we know nowadays, the cooling demand is typically going to be much higher. So size for the heating demand and typically size more smaller ones, and it will operate much more efficiently because you want them running simultaneous heating and cooling as much as you possibly can. And then you can deal with the peak load with a separate chiller. And this is what we've done with quite a few of the projects, such as your new Salesforce, for example. Thanks.
Thank you. Any more questions for Peter?
In the corner? Red one?
Yeah.
Well done, Peter. Is there much of a difference in capital investment between?
No, it's not really. In fact, you should be saving, because unlike your boiler and your chiller and pipework typically going to different places, there's a couple of things of consideration. But of course, the multifunctional heat pump is a bit more expensive than having a chiller or a heat pump. The exact percentage I couldn't tell you off the top of my head, but it certainly wouldn't be very substantial, because you've really only an extra couple of valves and of course the software. Now they do of course charge for the manufacture of it, but the additional cost would not be much more than, like I said, a typical chiller or heat pump, but you are saving in relation to your boiler. Now some consultants will allow for a boiler as a backup, because remember, as I said, when the ambient temperature gets very low, the efficiency will drop off. So there is a point where you might say, well, actually, I'm better off using a boiler now at this point. But however, again, to go back to this gentleman's question about the NZEB, you're typically trying to avoid fossil fuels to achieve your NZEB. So if you don't have a boiler, you need to, of course, size for your low ambient. The other thing in relation to cost is with a multifunctional heat pump, on the heating side, again, it's not like a boiler where you would have typically had a very high delta T. You might have had a 65 degree supply, return of 45, maybe a 20 degree delta T. With multifunctional heat pumps, the max delta T is about 10. We would typically recommend a max delta T of about 8 to keep well within your limits, your tolerances. And any of you engineers have gone to college should remember your Q equals MC delta T. So if you have your capacity divided by your delta T, your flow rate will increase. So if you have a smaller delta T, you will have a higher flow rate. So if you have a higher flow rate, your pipe diameter will increase. So your initial capital cost in pipe work on the heating system shall be slightly higher. But of course, that becomes quite negligible in relation to the energy savings that you're making forever after.
Then, can you retrofit old systems with this? Because, or would you have to start from scratch, really?
Again, for the very point I just made in relation to pipework sizing, retrofitting a heat pump, you would typically have to oversize your pump to overcome your smaller diameter pipe. From an engineering perspective, it's not really good engineering design. They're really made for new systems. It can be done, but it's not so straightforward.
Okay, Alan, time check. We can take one more.
Last question.
Yeah, last question.
Thanks. I just quickly was wondering, just when you said there about retrofitting, just wondering, do they work well with district heating systems?
I don't know yet, but we're talking to a couple of consultants about centralized district heating systems. Come back to me in a year. I'm not sure. But yeah, the logic is the same. So yes, they should.
Okay, thank you,
especially
Peter.
Of course you have simultaneous heating, cooling requirements for us.
Thanks again.
Okay,
thank you, everybody. And as we're just a small token, Peter, on behalf of the Mechanical and Manufacturing Division and our chairman here, Professor Dermot Bravazon in the front here, just a small token presentation.
Thank you very much.
And thank you very much for coming on and presenting.
Thank you very much.
And thanks everybody for attending, and our online viewers, thank you for joining. Okay, good evening everybody.